it shows that there's kind of more work to be done on the interpretations of quantum theory, right? It shows that we're not just stuck with these big three options, right? I think the main thing that I've learned from these last few years of research during my PhD has been that the arguments stack up for saying that transformation that we need to unlock a satisfactory understanding of quantum theory is to invert our traditional understanding of events and influences, to stop thinking about causation as merely a relation between events whereby one brings about another, to start thinking about causal influences as fundamental, and to start thinking of events, and ultimately all of this reality that we live in, as being something that emerges from those causal influences. When you've got all this new information that comes from recent quantum foundational research, there's just new things you can do, which is pretty exciting.
Hi, welcome back to the Quantum Foundations podcast. I'm Maria Villaris. I'm a PhD student researching the foundations of quantum information here at the University of Oxford. Today I'm joined by Nick Ormrod, who is a PhD student in the Computer Science Quantum Group, also here at Oxford. In the previous episode, we talked with Nicetu Tibal-Vidal, who explained the topic of locality. And in this episode, we're going to be talking about whether reality emerges from causal influence, which is the topic of Nick's PhD research. Thanks for joining us. As you may have seen from the previous episode, this podcast has two parts. One part is explaining the topic in non-technical terms that hopefully anyone who is interested can understand, and that's the part that's in this episode today. And then there's also a part two, which goes into technical mathematical detail for people who have had some introduction to quantum mechanics and want to see the mathematics of what we're talking about. So that will be posted in a separate episode. So thank you for joining us. And to start with, Nick, could you just tell us a bit about your background and how you ended up doing a PhD in quantum foundations here at Oxford?
Yeah. So I guess that when I was a pretty small kid, say like 5 or 6, I was really into sort of big questions about the universe and stuff like that, and would often bother my parents with that kind of thing. But probably by the time I was like 10 or 11 or something like that at school, and I'd done a bit of science, I didn't like science very much. I thought science was basically for people who might be quite smart but are maybe slightly boring, not very creative people kind of thing. And I was more into more open-ended subjects like English and stuff like that, or history or something like that. But then what I realized over time, I think partly as a result of watching some YouTube videos like yours, and also reading, I remember for like my 16th birthday, my aunt got me this, she got me Einstein's book on relativity theory, where he explains it for the layperson in sort of at the conceptual level. It sort of struck me that actually science is not just about calculating, it's about like transforming our old ideas into like radically new ideas that previously would have been difficult for us to imagine. And as soon as I understood that that's what it was, I got really excited about it. So I did physics and philosophy for my undergrad at Bristol, and really liked that course. That was great because when you're doing both the physics and philosophy, you get to sort of integrate the maths and the conceptual side quite nicely. And I basically, I started to really, really love the interplay between the sort of conceptual style of thinking that you learn in philosophy and what that can tell you about physical theories. And I basically wanted to just do more of the same of that, essentially. And so that's why I ended up doing the PhD here.
Great.
Yeah.
I don't know about anyone else, but until I spoke with Nick recently, I didn't know that Einstein had written a book for the layperson, so that's cool to know. Cool. So, thanks for the introduction. So, today we're going to be talking about this idea of reality emerging from causal influence. So, before we dive into the details of that, could you just give us a kind of overall summary of what the main idea is here?
Yeah. So sort of the main, I guess the most important bit of this research that I've been doing in my PhD that we're going to discuss today is this theory that's called the theory of causal balance. And that theory is what you might call an interpretation of standard quantum theory, where really what I mean by an interpretation is just like a more precise version of the theory. A theory that doesn't rely on this unanalyzed concept of measurement or anything like that. So it's an interpretation of quantum theory called the theory of causal balance, and it's based on this idea that actually causal influences are fundamental, and events, and ultimately the whole of reality, everything that we experience, emerges out of those fundamental causal influences. And that's a difficult idea to get your head around, but I think an analogy can help. So the idea from the theory of causal balance is that the world is a little bit like a spider web, essentially. So picture a big, messy, complicated spider's web. And the idea with this spider web is that the threads in the spider web represent causal influences, and so the web itself is the causal structure.
Right.
You've got this web, and there are various points on the web where various different threads meet each other at a point before they diverge and they shoot off in all sorts of different directions.
Yeah.
Many, many different points where the threads meet, and we're going to call those points junctions, right? So there are junctions in the spider web. Now, every junction is different. It's different because every junction is connected to the different junctions in different ways. So one junction might be connected to loads and loads and loads of other junctions all around it. There might be another junction that's only connected to like one or two. There will be some junctions towards the bottom of the spider web, others towards the top. The different junctions are different in general because they've got different connectivity to the other junctions. And what that means is they play a different role in the causal structure.
Right.
Okay. Now, at this point, I'm going to add something to this picture, which might force me to stretch the analogy a little bit. We're going to add events into the picture. So, what's an event? Well, we often talk about events as being things that happen, things that we go to. So, like a music festival is an event. An election is an event. Us recording this podcast is an event. But all of those events that I mentioned are relatively large. They occupy relatively large portions of space and time. They're extended.
Yeah.
They're made out of much smaller events, like the event of me saying a sentence, for example. But we could go smaller and smaller and smaller.
Yeah.
Now, the idea with this theory is that ultimately all of the events that happen in the world are made out of tiny events that take place on the junctions of the web, right? There are things happening, there are events happening on those junctions in the web, the places where the threads meet. And they happen as a result of the unique way that that particular junction is sort of pulled on by all the other junctions. But remember, every junction is different because it plays a different role in this web of causal influences. Its connectivity to the different junctions are different. And what that means is you can have different types of events happening at all the different junctions. Now, it's probably worth saying at this point that this is not a deterministic theory, it's a probabilistic theory. So it's not that the causal structure, it's not that this web of causal influences determines exactly what event is going to happen at a given junction, but it determines what the set of possible events are. It determines the events that might happen, and it also gives you the probabilities. The causal structure, the web, gives you the probabilities for the different events that might happen at a given junction. And yeah, that's basically the worldview that the theory is trying to advocate. Yeah.
Cool. So, yeah, to try and recap this analogy, the idea is that so we have this spider's web. The threads are like when something causes something else. Or what's the connection?
In the end, yes, but well, yes. Okay, so that's a good question. Although I'm using the word causal influence, I probably mean something slightly different by that to what we would traditionally mean. Because what we are doing with this theory is we're advocating a kind of transformation in our concepts, right? So for example, time to a physicist now,
Mm-hmm.
because of Einstein's theory, it means a different thing to what time meant in the 19th century.
Mm-hmm.
We use the same word, but what we
Yeah.
mean by that word is different since
Yeah.
Einstein's theory of relativity.
Mm-hmm.
Similarly, what I'm trying to argue, and what my PhD supervisor John Barrett is also trying to argue, which I should mention, we developed this theory together.
Mm-hmm.
What we're arguing is that in the same way that we've transformed what we meant by time in the past, we should transform what we mean by causal influence. Now, it's very natural to think that causal influence is about one thing causing another thing.
Mm-hmm.
In which case you're sort of starting with the things, right? And then you're
Yeah.
defining the causal influences in terms of the things.
Yeah.
We, on the other hand, are trying to say that causal influences are fundamental. We actually want to be able to define things in terms of the causal influences.
Mm.
This is why I kind of like the web analogy,
Mm-hmm.
because those junctions, right?
Yeah.
They're just the place. They're just the places where the threads intersect.
Mm-hmm.
It's not like the spider when the
Yeah.
spider's making his web starts by putting down the junctions and then
Yeah, then
builds
connects
these
them.
connections. No, the
Mhm.
junctions are created by the intersection between the different threads.
Right.
Yeah. So where do things come into the picture?
Mhm.
Well, because of the unique way that a given junction is sort of tugged on
Mhm.
by the threads and ultimately by the other junctions, that sort of creates
Mhm.
certain events that happen at that junction.
Mhm.
And things, you and me, the table, the chairs, ultimately everything, music festivals, elections and so
Yeah.
on, they're all ultimately made out of these events that happen at the junction. So this is a view in which causal influence is fundamental and the things that influence each other are coming out
Mhm.
of the influences.
Yeah, I see what you're saying with the analogy now. So you have these threads of the causal influences are the fundamental thing that kind of
Yes.
comes first. And then you get these intersections emerging where, like you said before, some of them have like loads of threads connecting them, some only have a few, and you get these
Yes.
differences. And then emerging from that, you get these events happening at these intersections, and in your theory they happen in this
Yes.
probabilistic way that
Yeah.
depending on the structure of the causal influences surrounding them, the events happen with certain probabilities. Different things may happen at those junctions.
Exactly. And those probabilities are kind of determined by the causal structure too. Yeah.
Mm-hmm.
Yeah.
Right. Yeah. And if I'm trying to think, like, what does this mean for my view of reality? Like, if events are happening probabilistically,
Yeah.
emerging from causal influence, what kind of worldview does this lead me to?
Well, certainly one of the aspects of this worldview is simply that it's probabilistic. There's no predetermined fact of the matter about what's going to happen. There is genuine chance in the world.
Mm-hmm.
But it's chance that is determined by the causal structure.
Mm-hmm.
But I guess I guess the even more transformative aspect of it really is just the idea that things are not fundamental, or events are not fundamental. So I mean, what would be a good thing to talk about? So I mean, it's kind of a funny inversion, I think, of our traditional conceptual framework, because I think out of influences and events, right, it's really events that most people have an easier time understanding. An event like the event of like me striking the cue ball in a game of pool, and then the event of the 8 ball falling into one of the holes or something like that. We understand those because we see them, we hear them, we maybe even feel them sometimes, right? We have sort of a direct sense experience of that.
Yeah.
Now, when I strike the cue ball and it strikes the 8 ball and the 8 ball goes in the hole, we do feel a strong conviction that there's something called causal influence that's at play there, right? We don't think it was some kind of coincidence that the 8 ball ended up falling in the hole, right? We think that it was caused by what I did. But when we try to pin that idea down, we actually struggle to do it quite a bit. And it's created a great deal of philosophical controversy over the last few centuries, or maybe even longer than that, what exactly it means for one event to cause another.
Yeah.
And I don't, I certainly don't want to weigh in on that, because we're sort of already transforming the concept of causation in a different way here.
Yeah.
But without sort of getting into that discussion too much, what's clear is that events are kind of the things that we seem to more directly experience, and causation is a thing that's difficult to define, but somehow we normally define it in terms of events, right? Whereas this is quite a different idea, where the influences are actually the kind of fundamental things, and the only reason why there's, forget about this claim that me striking the cue ball causes the 8 ball to go in the hole. The only reason why there is a cue ball to be struck is because that cue ball is made out of a bunch of events, and those events were shaped by those causal influences, were shaped by the way that the threads pulled it at that junction in the web of causal influence.
I like this image of the causal influences shaping the events, and cool. And so this theory you've kind of built up upon some previous work that was done on causation. So could you talk a bit more about these traditional ideas around causation, and how your ideas built up on these, or modified them, or connect with them?
So I think it is a big break from this traditional idea of causation as being defined as this kind of relation between events. So sort of again, traditionally you might think that the first thing that we talk about, the first thing that we kind of understand are the events, and then when we're trying to explain causal influences, we explain them in terms of events, or we define them in terms of events, whereas we're kind of doing the opposite thing. We're defining events as that which emerges from causal influences. But I guess what might be helpful for people is to see how our idea of causation is creating the events connects to this more traditional idea of causation as making one event follow from the other, right? Because that is something that you need to do, right? When you're proposing a conceptual transformation like that. I used the example of time and Einstein's theory of relativity. So it was fine for Einstein to propose a transformation in our concept of time, but in order for that to make sense, he had to explain how it related to the Newtonian concept of time that came before it, right? Because if there was no relation whatsoever, then there would just be no reason to use the word time, right? That would just be gratuitous. You should just come up with a new word, right? So although we are suggesting that we should change what we mean by the word causation, our new sense of it does have something to do with the old sense of it, and the clues to that are in what we talked about before, about causation shaping not just the set of events that could possibly happen, but also determining the probabilities for events happening. Right. So, and it doesn't just determine the probabilities for an individual event to happen. It determines the probabilities for whole sets of events to happen at the different junctions. Right. So it determines joint probabilities over all of the events in this.
Right. So, say using the music festival analogy, is it as though you have a set of events that could happen at this music festival, and the probability of one set of music festival events as opposed to another.
So let's say that the headline band of the festival, either they've rehearsed or they haven't rehearsed. Right? And either of those counts as an event, right? Rehearsing is an event, and not rehearsing is also an event, right? Both of these, again, are events that are made up of many smaller events, but whatever, that's fine. So the headline band either rehearses or doesn't rehearse, and their performance either goes very well or terribly. Okay, I don't know exactly how we define precisely what it means for a performance to go well, but let's assume that we've done it. Okay, so we've got these two sets of events, right? Rehearsal or no rehearsal, and great performance or not great performance. Now, the causal structure, those events are only capable of happening in the first place because they were shaped by this web of causation. But also, the causal structure is determining the probabilities not just for individual events to happen, but for pairs of events to happen. So the causation determines the probability that they rehearse and it goes well. It determines the probability for they rehearse and it goes badly. Determines the probability for they don't rehearse and it goes well. Or they don't rehearse and it goes badly, right? There's 4 pairs of events. We get joint probabilities for all of them.
Right,
And, okay. So we might expect that there's a relatively high probability for they rehearse and it goes well. And there's a relatively high probability for they don't rehearse and it goes badly. Or it goes not well. There's a relatively low probability that they rehearse and it goes badly. And there's a relatively low probability that they... Did I just repeat what I said? Maybe I did. So there's a relatively low probability that they rehearse and it goes badly, and there's also a relatively low probability that they don't rehearse and it goes well. That's what I meant to say. Okay, and so what that means is that if we assume that they rehearsed, that is, if we say, given that they rehearsed, given that that event happened, then what's the updated probability for whether the performance is going to go well or badly? We're going to find it's very likely that the performance goes well. Whereas if we make the opposite assumption, if we say, let's assume that they didn't rehearse, then what's the probability that the performance goes well? Then we're going to find it's a low probability that the performance goes well and a high probability that the performance goes badly. And so we see that causation, in the end, does end up playing this role of like making one event follow from the other. But it only plays that role because it sort of shaped those events into existence, including their probabilities in the first place. So to sort of summarize it, you might think of the traditional concept of causal influence as being like some kind of ruler or some kind of queen, right, that's dictating that, this event must follow from this event, right? It's commanding what events have to follow each other. Whereas what we're saying causation is kind of this creator, right? It's shaping the events and their probabilities in the first place. And so we're not denying that causal influence plays its sort of time-honored role of queen, but we're saying that it only does so as a result of the fact that it plays its more fundamental role of being the creator of events and ultimately the creator of reality.
So it creates these events, including these joint probabilities, and kind of you can connect up with the traditional conception of causation by seeing how these joint probabilities, you can see this traditional causation in those joint probabilities in the sense that they connect in the way that you'd usually expect from traditional causation, but with this shift that's coming from a different mechanism but leading to that traditional causation conclusion as a kind of emergent thing. Exactly.
And maybe we could sort of refine the point a bit more by again invoking this comparison with relativity theory, right? So an important step in developing the theory of relativity was you had to show that for your viewers who are familiar with these terms, you had to show that at low velocities the Lorentz transformations sort of reduced to the Galilean transformations. But the more layman's way of saying that is you had to show that as long as nobody's moving very quickly relative to each other, if relativity theory is true, then that means that Newtonian mechanics is very close to true, right? And so you sort of see the structure of Newtonian mechanics, or at least something very close to the structure of Newtonian mechanics, that is embedded in the theory of relativity. what we would like to do with our theory, and we haven't done this explicitly yet, but this is sort of ongoing research.
Yeah.
We would like to take our sort of traditional theory of causation, which is the framework of, probably the best thing to take would be Judea Pearl's framework of causal modeling, which has been pretty influential over the last few decades. We would like to show in a rigorous sense how in the appropriate sort of regime, when you take our notion of causal influence and our theory of causal balance, you recover Pearl's theory of causal influences.
Yeah, cool.
Yeah,
I hadn't thought about it that way before. And we get the same thing in quantum mechanics, right? We have this, correspondence principle. If you expect, you have to get the, traditional classical thing emerging as an approximation when you go to scales that we'd usually use classical physics to describe.
Or also closely related to that, Ehrenfest's theorem, saying that in the appropriate kind of circumstances, the expectation values of your observables are going to evolve in exactly the way that you would expect the corresponding variables to in classical physics. It's exactly that kind of idea of we're proposing a theory that is radically different, sure, to the theories that have come before. But the idea is we can explain why it is that we weren't so silly in the first place to come up with those theories. We can we can zoom into our theory in the appropriate kind of circumstances, and we can find those old theories hidden inside its structure.
Yeah, cool. So we've talked quite a lot about causation and this shift in in the view of the connection between events and causation, but we've not talked much about quantum mechanics yet. So could you tell us a bit about how this theory emerges from quantum mechanics, and maybe focusing on the you mentioned it's an interpretation of quantum mechanics, and we have this famous measurement problem, which is the commonly mentioned as the problem of standard quantum mechanics. So can you tell us a bit about how your theory relates to the measurement problem?
Right. So the short answer is that the theory is intended as a solution to the measurement problem. Okay, but how? What is the measurement problem and how do we solve it? So the measurement problem is actually like a whole mess of different problems that are all kind of related. They've all got to do with measurement, of course. Maybe I can mention a couple of them briefly and give a sense of how they, how what we're doing relates. So maybe we could start with a fairly specific aspect of the measurement problem, which is often referred to as the preferred basis problem. So so it's called the preferred basis problem. Now, I guess many of your viewers will be aware that the sort of mathematical spaces in which quantum theory takes place are vector spaces. More precisely, they're Hilbert spaces, but Hilbert spaces are examples of vector spaces. Excuse me. And an example of a vector space could be the sort of ordinary 3D space that we live in, as long as you're willing to add an origin to it, but let's say that we are. So let's say that here is the origin of my vector space. The idea here is that every point in space, or every point in this room, say, we can think of as an arrow that points from the origin of my coordinates to that point. And if we want to be able to sort of build an arbitrary one of these vectors, or if we want to be able to sort of go to arbitrary points in this room, we can use something called a basis. And this is a basis, right? It's a set of vectors. We'll assume that they're sort of at right angles to each other. They're the set of vectors which, if you're allowed to sort of go in the directions of the vectors individually, then that allows you to go in any direction you want to and ultimately get to any point. So if I'm only allowed to use these three vectors and I want to get over here, from the origin over here, then that's easy. So first I use this vector to go this way, and then I use my forefinger to go this way, and then I use my thumb to get up here. So just with these three vectors, I can build up any other vector that I want to. But the thing is that I could also have used a different basis. I could also use these three vectors or these three vectors, and there's an infinite number of different bases that I could use.
Yeah. Yeah, so we can think of the vectors as, like arrows that are kind of giving you a boost in a particular direction.
Yeah.
And with 3 different directions you can cover 3D space. And so that's the kind of we're used to like an X, a Y and a Z axis all being perpendicular, and you can build up your vectors as arrows along those directions. And like you said, you can use those 3 to get to between any point in space to any other point in space in this room.
Yeah.
But we could imagine those kind of 3 axes being rotated some way, and we'd still be able to use them to get to any other point.
Exactly.
Or shift the angles a bit, and we can still use them.
So everybody knows that if you're able to go forward and backward and left and right and up and down, then you can go anywhere you want.
Yeah.
But if I just rotate myself like this, then suddenly the meaning of, up and down is still the same, but my meaning of forward and backward is different, and that corresponds to using a different basis for building up my vectors, if you like.
Mm-hmm.
Now, the vector spaces in quantum theory, they're not really supposed to be, at least on the sort of standard way of thinking about it, they're not supposed to be the physical space that we live in, right? They play a different role. And the role that they play is that every different basis, right? Every different way of sort of, carving up that vector space into this set of perpendicular vectors, every different basis corresponds to a different observable property of the system. So for one type of quantum system, one basis corresponds to the position property of the particle. So like, it's kind of counterintuitive, but it's like this vector corresponds to one position, this vector corresponds to a different position, this vector corresponds to a different position. And a different basis corresponds to the momentum of the particle. Okay, it's actually slightly more subtle than that because the individual positions don't correspond to individual vectors, but it's a good enough kind of approximation for the purposes of this discussion. So different bases correspond to different observable properties of the system. But your viewers might have heard of the uncertainty principle, right? Which says that you can't know the position and the momentum of a particle at the same time. Or put a slightly stronger way, you might say that the particle cannot have a definite position at the same time that it has a definite momentum.
Which is really weird and surprising.
Yeah. And if that's true, right, if it's true that it can't have all these this infinite set of different properties at once that correspond to the different bases, and if it's got some properties nonetheless, then it must have the properties that correspond to a particular basis, right? But the question is, why should any basis ever be preferred over any other? So suppose your particle at a given moment in time happens to have a definite position. So it doesn't have a momentum, but it's got a position. The question is, why does it have a definite position and not a definite momentum? What's so special about that basis as opposed to all of the others? It's the same question if it's got a definite momentum, right? Why has the momentum basis suddenly become special? This is the preferred basis. Why should any basis be preferred over any other? What makes it special?
Yeah, because when we're kind of writing out our quantum state, so when we're trying to describe a system using quantum mechanics and we write down what state it has, we could write it using, like, in terms of any one of these bases. Like, we could write it in terms of the position or in terms of the momentum.
Right.
And there's kind of no obvious reason why we would write out the description of this quantum system in one of the ways compared to the other way. And so there's this kind of ambiguity where it doesn't tell us, like, well, what should we how should we see it behave in being definite in a particular one of those bases.
Exactly. So our answer to this problem is to say that a preferred basis is preferred because it's preferred by, guess what, the causal structure. So when, I wasn't going into the mathematics of it when I was sort of giving you that overview. But when I said that, at the junctions, these events happen depending on the role that the junction plays in the causal structure, right? Depending on how the other junctions pull on it. I mean, an example of an event might be, it might correspond to what we would normally refer to as a particle taking a definite position, right? So maybe the junction over here has like the event of a particle having a definite position, whereas the junction over here might have the event of some particle having a definite momentum, right? So when causal influence is choosing, if you like, or singling out the set of events that can possibly happen, what it's doing is it's choosing a preferred basis, and the different elements of that basis represent the possible events. Okay. In the interests of correctness, I should say that in general it's not choosing a basis, it's choosing a more general thing called a projective decomposition, which maybe we won't go into here because but you know, if you know, you know, it's a generalization of this idea of a basis. So in a sense that's kind of the essence of the theory. We're solving the preferred basis problem by saying a preferred basis is picked out on a junction by the way that that junction causally interacts with the other junctions. Right.
And how can I connect that back to thinking about what we see in the world? We have this kind of emergence of our approximately classical day-to-day life, and things seem kind of picked out in the position basis.
Right.
Yeah, do you have any comments on how it relates to this, to what emerges in our physical reality?
Yes. So indeed, the explanation of the fact that the position basis tends to generally be preferred, or at least something very close to the position basis tends to be preferred, is that, you know, the structure, the web has the right causal structure such that it does pick out the position basis. It corresponds. I'm not really sure how to. I'm not really sure if I can add much to that without going into technical detail. But if your viewers are, for your viewers who are a bit more familiar with quantum theory and are used to the idea of a Hamiltonian, which gives you the dynamics on the usual approach to doing quantum theory, typical Hamiltonians kind of single out the position basis as being preferred because they're sort of defined in terms of the position basis in a particularly nice way. And there's a similar kind of idea here. So in standard quantum theory, the Hamiltonian sort of plays with position in a special way. In our case, the causal structure of the world is going to be such that it sort of leads to the position basis quite often being preferred. Yeah.
Cool.
Yeah.
Yeah, nice. And there's various, when we're talking about the measurement problem, so we've talked about this aspect of picking out a particular basis. Yeah. And another aspect that comes up in this set of measurement problems is the role of the observer when you observe something, what you see, and could you talk a bit about the implications of, or how your theory connects with observers and these aspects?
Yes. Yeah. Okay. Yeah, so the short answer is that we hate observers. We want to get rid of observers.
Okay.
The slightly longer answer than that, because the short answer isn't really accurate, is we don't hate observers, but we want to treat observers the same way that we treat everything else. We want to be democratic about things.
Yeah.
We want the observer to be just another part of the theory. Yeah. That's how it is in relativity theory. That's how it was in Newtonian mechanics. This is the way that it generally is in physics. Yeah. But it's not this way in quantum theory, and this is really the scandal of quantum theory, right? Quantum theory is it's a really interesting theory. It's really interesting that we've come up with standard quantum theory because it is simultaneously so impressive and so embarrassing. So it's so impressive because it predicts phenomena so well, so accurately. Its best predictions seem to diverge from experiments so little that one figure I read was like 7 parts in 1 trillion is like the biggest we think it's possible for the quantum predictions to be That's the largest possible discrepancy between our predictions and what really happens.
Yeah.
So 1 in 7 trillion, that's like, there's like 12 zeros there. There's a lot of zeros.
Crazy impressive.
Crazy impressive stuff.
Yeah.
So it's incredible that human beings have managed to do that. But on the other hand, what's also remarkable is that for all of its predictive prowess, standard quantum theory is awful at explaining why those predictions are true. It certainly does not explain the validity of its predictions in terms of like this clear and precise picture of the physical world. And I think it's a bit of a problem sometimes when it comes to pedagogy and the popularization of quantum physics sometimes. And I can understand why it happens, right? Because it's difficult to get into these weeds, right? These are very kind of like subtle issues. But, sometimes people will say that, like quantum theory tells us this thing about the world, right? Quantum theory tells us that this thing is a wave and a particle at the same time, right? Or quantum theory tells us that there are these virtual particles that pop in and out of existence. Doesn't really tell us anything. Like, what it does is it provides us an algorithm for transforming one thing that we've seen already into predictions for another thing that we're going to see. But the whole apparatus it uses to do that is just too vague to give us any clear account of what's happening at all. These are all, particles popping in and out of existence and waves of particles and stuff. These are all useful images to have in your head sometimes when you're using the standard quantum theory. That's not the same thing as saying that like quantum theory tells us that the world is like that. It's too vague to be able to tell us anything really. Okay, and it's vague because its axioms include this word measurement, and it's not clear exactly what that means, right? And it's a really backwards thing when you think about it, because quantum theory is sort of trying to talk about these tiny microscopic particles, but the story that it tells you about the microscopic particles depends on you already understanding the concept of measurement, even though measurements are the sort of thing that you do, and you're made out of a lot of particles, right? And so it's just impossible to get like a clear and sort of self-reliant account of what these particles are doing when you constantly have to refer back to measurements which themselves depend on the particles. So it's a very unfortunate situation that we find ourselves in the standard quantum theory. And that, in a way, I think is the most fundamental measurement problem, right? It's the fact that although we've got a great theory for prediction, we don't have a good theory for explanation, and that's because of the way that it relies on the concept of measurement. Now, all of these ideas that I'm telling you about causal influences being fundamental and events emerging from them, and all of this kind of thing, we can use analogies like the spider's web thing in order to like try to get you the general idea. But ultimately, all of this stuff is anchored in the equations of a precise physical theory called the theory of causal balance. It's a theory which has axioms which say physical things, but it sort of expresses them clearly through the language of mathematics. It's a precise framework that allows you to generate precise predictions, but also it enables you to pin down the description of reality, and it enables you to explain reality in terms of that. So we no longer have this theory that axiomatically depends on measurement. We've now got this theory that gives you a certainly counterintuitive and certainly very strange, but it at least gives you a picture of what the world is like.
So it becomes, so in this theory, things are made precise in a way that they're not in standard quantum theory, and the theory of measurement is made precise in your theory. Or actually, so I'm not sure if I would agree with that last point. So if we think about, forget about quantum theory for a second, and if we think about Newtonian mechanics, does Newtonian mechanics give you a precise definition of measurement? I would say that it doesn't, right? Because how do you do it, right? How do you define measurement in terms of Newtonian mechanics? You can probably imagine that different scientists would give you slightly different definitions, and this isn't that weird a thing, right? It's in the same way as if there was a big mountain, right, and you had to come up with what the definition of that mountain was, and you had to say exactly when does
when do the planes stop and when does the mountain begin kind of thing.
Mm-hmm.
It might the mountain might increase in a gradual way, such that there's no natural cutoff point for you to say when the mountain begins. And so if we're both asked to come up with definitions of the mountain, we might give slightly different definitions. Mm-hmm. And it doesn't mean that either one of us is wrong. Mm-hmm. Or if you're asked to give a general definition of like just what is a mountain, mm-hmm. and how is a mountain different from a hill, mm-hmm. we could make a cutoff point. I mean, I don't know what people say about mountains, whether it's like a kilometer or 10 kilometers or whatever. Mm-hmm. But there's no like obvious sort of cutoff point. And I think it's similar with measurements, right? Mm-hmm. It's not clear exactly what a measurement is. Mm-hmm. However, the idea with Newtonian mechanics is that, okay, it hasn't worked, but if it had worked, then the idea of Newtonian mechanics was that any scenario in which somebody is doing a measurement can ultimately be given this precise physical model in terms of a bunch of little particles bouncing against each other in the way that is dictated by Newton's 3 laws of motion. Mm-hmm. And similarly, the idea with the theory of causal balance, it's not to pin down the precise definition of measurement, because mm-hmm. I see no reason why we should be able to do that. Yeah. It's rather to just be able to, in any given measurement scenario, in principle, we should be able to give as precise an account of what's going on as mm-hmm. you could in the Newtonian case. Mm-hmm. A weirder account, but a more precise, but an equally precise one.
Yeah. So for any situation involving measurements, however you want to define measurements, for any situation involving them, you can then say, okay, what does the theory say about it? And you can precisely find out you can describe the situation at hand.
Yes.
Even though people may have different definitions of what they want to call a measurement, for any situation with any of these
in a sense it won't matter, because we'll have the model and everybody can agree that the model is the correct one. Different people can look at that model, and some person might look at that model and say, oh, the measurement's what's going on over here, and someone else might say, no, it's what's going on over here, but mm-hmm. who cares, we've got the model, it's fine.
Yeah. Cool. And there's this idea that comes up, okay, so say if we think about a typical Schrödinger's cat type situation, where Schrödinger's cat, we have this situation of the cat enters this quantum superposition of being alive and dead because it's in this box, and it may or may not have been poisoned by some radioactive atom causing a vial of poison to smash and kill the cat or not, with some 50-50 chance. And then an observer looks inside the box and sees the cat alive or dead, and there's this kind of narrative of inside the box the cat may or may not be alive or dead, or maybe it's both at the same time, or we can't know whether it was alive and dead. Could you tell us a bit about what your theory means for that kind of situation?
Right, what do we say about the Schrödinger's cat? Yeah, okay. So maybe it's best to recap that description of the Schrödinger's cat experiment a little bit further. Mm-hmm. So let's say that we start with this electron that is in a superposition of two spin states, mm-hmm. spin up and spin down.
Mm-hmm. So spin is just a property that electrons can have.
Yeah. And what we do is we make the spin of the electron interact with this hammer that can smash open this bottle of like gaseous poison, which is going to kill the cat, right? Mm-hmm. But we make it interact in such a way that that's only going to happen. The poison is only going to be released if the electron is in the spin-up configuration.
Mm-hmm. Yeah.
So we can do that, and then there's going to be sort of two branches of your overall wave function, where in one of them, the electron is up and the poison has been released, and as a result of that, the cat's going to be dead. Mm-hmm. And in the other branch of the wave function, the spin of the electron is going to be down, mm-hmm. and the poison is not going to be smashed, and the cat is going to be alive. At least that's a description that you can come up with using standard quantum theory.
Mm-hmm.
The description with our theory looks quite different because actually we're not really using the wave function. We're not using the wave function as a description of reality.
Mm-hmm.
We're talking about events.
Yeah, so we've shifted description with your theory.
Yeah. And essentially, there are going to be a bunch of tiny events on that web of causal influence,
mm-hmm.
which together determine whether the cat is alive or dead. Right? So if the cat is alive, then it's going to be standing up.
Mm-hmm.
And so, the positions of various of the particles are going to be relatively high up, whereas if it's dead, it's going to be lying on the floor and they're going to be lower down.
Mm-hmm.
Right? And ultimately, all of those events have their origin at the junctions of this web
mm-hmm.
of causal influences. Now, in order for this kind of superposition to be preserved,
mm-hmm.
in order for the superposition to be preferred, the events that are picked up by the causal structure at those junctions
mm-hmm.
would have to not correspond to definite or approximately definite positions.
Right.
But in actual fact, what's going to happen is that preferred events are going to give you these definite positions, and therefore it will, the causal structure is going to force it to be the case that either the cat is alive or the cat is dead. It's not going to be predetermined which one,
mm-hmm.
whether the cat is alive or dead, but it's going to be one or the other, because that's the basis that is going to be selected as preferred
mm-hmm.
by the causal structure. So in other words, it forces something which, using the standard quantum theory,
mm-hmm.
We would describe as collapse, essentially.
Mm-hmm.
Or it's not exactly collapse, but it's something that viewers who are familiar with standard quantum theory, they will recognize a similar sounding idea from
mm-hmm.
collapse.
Yeah, so you get this effective collapse happening probabilistically from the causal structure. So the causal structure leads you to probabilistically have the cat dead or alive.
Yeah, so there's a subtlety here.
Mm-hmm.
On the one hand, yes, that's absolutely the case. But it's a bit tricky when we're discussing the notion of collapse. It's a little bit tricky because when you talk about whether an interpretation of quantum theory is unitary or involves collapses.
So, I guess unitary means it's all everything's fully reversible, you don't have any irreversible collapse. So, a measurement can be reversed, essentially.
Well, yes, but it does. But on the sort of usual way of thinking about quantum theory,
mm-hmm.
you, at least a part of your description of reality, whether or not it's a complete description, is this quantum state
mm-hmm.
that evolves one way or the other through time.
Yeah.
That's not the picture that we have here. On our theory, there is no quantum state of the universe.
Right.
There's just a bunch of events. It doesn't mean we don't use quantum states, because actually all of those events are associated with quantum states.
Mm-hmm.
But if there are any quantum states at all, it's more like there's this big mosaic of quantum states. There's this patchwork of them that are associated with, ultimately, with individual junctions in that web of causal influences.
Right.
Right?
Yeah.
So there's no quantum state of the web, for example. That's not how the web works.
Mm-hmm.
And so that's why it can be a little bit awkward when discussing about collapses
mm-hmm.
versus unitary evolution, because normally what people have in their head
mm-hmm.
is that if the interpretation of quantum theory is unitary, that means that the state of the universe is always evolving unitarily through time.
Mm-hmm.
Whereas if people think about an interpretation featuring objective collapses, then what that means is that it's often evolving unitarily, but then sometimes that unitary evolution gets interrupted, and the quantum state
mm-hmm.
sort of like immediately discontinuously sort of changes from being one way to being a different way. Now, this whole discussion kind of isn't immediately applicable to our theory because we're not picturing the world as this unitarily evolving state in the first place.
Yeah.
Now,
right.
There's a sense in which our theory can nevertheless be said to uphold what we would call the universality of unitary evolution. There's a sense in which it can be said that all evolution is unitary, according to this theory.
Which means that you can apply kind of the laws of quantum mechanics at all scales to all situations.
Yeah, indeed. What it means for us is that if you want to assume that some event has happened over here in the web of causal influences, and then given that assumption you want to calculate the probability for an event that's happening up here in the web of causal influences, then you get the correct answer by assuming that unitary evolution has taken place in between these 2 points. So that something like the unitarity rule from standard quantum theory gives you the right predictions in our theory. And that's the sense in which all-time evolution is unitary.
Yeah.
But there's also a sense in which you sort of see the idea of collapse in our theory because in this Schrödinger's cat example, because of those causal interactions that take place when the poison is released and it spreads out, or it either does or doesn't, depending on the spin value of an electron, those causal interactions are going to force reality to be one way or the other. And when you put it that way, it sounds a little bit like collapse. But as I say, these words are a little bit difficult outside of the context of more traditional approaches to quantum theory in which the whole world is this big quantum state.
Yeah, so you're kind of completely shifting the underlying reality that we're thinking about in a way. But you get these kind of ideas we're more used to about collapse emerging in some sense in your theory when you look at its consequences. But the kind of underlying mechanism is completely different to the standard way of thinking about quantum theory.
Exactly, and you were asking earlier about what are the ways in which this theory is kind of challenging our more traditional assumptions about the way that reality works. This sort of relates to a significant point there, which I suppose I didn't mention earlier, which is that, well, I suppose it was connected to what I was saying earlier, but we sort of, when we do physics, we're very used to the idea of talking about dynamics and things evolving and changing. But usually what we mean there is that there's some sort of state, there's some sort of way that things are, and what change means is that you're changing the way that things are. You're evolving the state, right? Whereas for us, paradoxically, you begin with change, right? That's the fundamental concept, and the idea of the way things are, the thing that changes, that emerges from this more fundamental idea of change. And this is one of the things that I'm proud of about the theory, which is that very often people have proposed this sort of idea of kind of like change or influence or relations or something like that being fundamental. The earliest example I can think of was I've forgotten his name, but one of the pre-Socratic philosophers had this idea that fundamentally what the world was this sort of constant kind of change. And more recently you've got ideas like ontic structural realism from the philosophy of physics that describe sort of relations as being fundamental and things emerging from that. And I've always thought that these ideas are very cool. But often quite difficult to pin down. Right? So it's often quite difficult to say, okay, but what does that mean? What does it mean for the world to be based on change? How can you have change without something that changes? But with this theory of causal balance, we do have this precise mathematical theory which gives you one possible answer to that question. And it might, it may or may not be an answer that you're satisfied with, but it's an answer.
Yeah, that's a cool way of thinking about it, that there's this, kind of ancient philosophical idea of, is change more fundamental than the things being changed? And it's kind of emerged from your solution to the measurement problem. Yeah. Cool. And we've kind of mentioned a bit these standard way of looking at quantum theory and the measurement problem.
Yeah.
So maybe could you talk a bit about the other solutions that are being proposed for the measurement problem that people have looked into, and why you are not satisfied with those, or with developing those, rather than what motivated you to look at a different solution rather than ones that have previously been proposed.
Yeah, okay. Good. So in my view, solving the measurement problem means coming up with a theory which is a precise physical theory that doesn't rely on any kind of vague, unanalyzed concept of measurement.
Yeah.
And a theory that enables you to recover the predictions of standard quantum theory, but also to explain them in terms of this precise physical picture. Now, if that's what you want, if what you're going for is this kind of precise physical theory, then it seems to me that there are still these three major options, if we're sort of ignoring the theory of causal balance, which people have talked about for a long time. So the big three approaches are, there's the de Broglie-Bohm pilot wave theory, which sort of has an interesting response to this idea of wave-particle duality that is popular in quantum theory, which is to say, actually, there just is a wave and a particle, and the particle is sitting on top of the wave, being guided by it. That is a pretty old theory now. David Bohm wrote this book about it in 1952, where he really introduced it, but the ideas go back further, even a couple decades, to de Broglie. Also from the 1950s is this many worlds approach, inspired by Hugh Everett, where, if you're doing your Schrödinger's cat thing, then what happens there is that there ends up being two different worlds, and in one world the cat's alive, in the other world the cat's dead. And there's also the objective collapse theories, which essentially say that there's always this small probability of a given particle suddenly kind of collapsing onto one definite state or another. And I won't try and describe those theories in any more detail or go into criticisms of them in any great detail, because they're talked about an awful lot. The one thing I suppose I would say about them is that, in a sense, you can make a pretty decent argument against those theories just by kind of pointing at the clock. They've all been around for a fairly long time. I think the newest one would be the objective collapse theories, but they're, I think, more than 40 years old now. And all of them are very far away to commanding anything like a kind of consensus. And that kind of alone sort of suggests that none of them are probably ultimately going to be the answer that we're looking for. Now, I don't know that that's the case. That could not be the case, but it seems to me that just the lack of their ability to really command a consensus so far is a good argument for exploring other options. And so that's really what we have tried to do with the theory of causal balance. What we've done is we've taken an approach to the interpretation of quantum theory that's very much informed by modern research from this emerging field of quantum foundations. Yeah. And we found that has put us in a position to develop these ideas which I don't think they would have been much harder to develop even only a decade ago, right? Because we're very much relying on understanding that the community has only developed in the last kind of 10 years or so, especially, for example, ideas about causation in quantum theory. There's been a lot of research into the past 10 years, and I think that's kind of made possible this sort of inversion of our ideas, where we say that causal influences are fundamental. Yeah, that's interesting. Yeah, that is kind of emerged from recent developments, and that's why now is the time that these things have come together in your theory. Yeah, absolutely. And that's in a way, I don't know whether the theory of causal balance is sort of I don't know whether it's correct. I don't know whether our idea of causal influences being more fundamental than events. I don't know if that's right. I think there are good arguments to suggest that it's a good direction to go in, but maybe it won't be the correct direction to go in. But what I find kind of encouraging about it, whether or not it's kind of correct, is it shows that there's kind of more work to be done on the interpretations of quantum theory, right? It shows that that we're not just stuck with these big three options, right? That there are alternative, precise physical reformulations of quantum theory. You might like it, you might not, but it's there, it's an option. And if we've been able to develop that option in the very recent past, then maybe there are other kind of approaches that can be developed by looking at some of the same insights, and that'd be very exciting too.
Yeah, that's a good point. So you don't just see this as itself being an interesting alternative to the big three. You also see it as it shows that there can be good alternatives that are interesting to think about, and that based on recent progress and taking advantage of new research.
Exactly. I'll be keen to argue that the theory of causal balance is a kind of promising direction for us to pursue, but in a way what's even more exciting to me is just its ability to show by an example that when you've got all this new information that comes from recent quantum foundational research, there's just new things you can do, which is pretty exciting.
And maybe we should just mention, a lot of people have heard of the Copenhagen interpretation and of this theory of quantum mechanics, so why is that not in these big three?
Right, that's not in the big three because it doesn't sort of count as what I'm calling a precise physical theory. This is okay, so there are different versions of the Copenhagen interpretations, and they all say subtly different things, but broadly speaking, the Copenhagen interpretation sort of just accepts the axiomatic dependence on measurement that standard quantum theory has. I mean, the Copenhagen interpretation it almost is standard quantum theory, and so it's not attempting to describe reality in terms of in these kind of precise physical terms. So it's not giving the kind of explanations that that I think that we should be pursuing in physics.
And probably almost the fact that there are these different versions of the Copenhagen interpretation almost adds to the point of it being quite vague. Although, having said that, there are different versions of a lot of these interpretations, so that is something you can say about everything. But it doesn't tell you what measurement does, so it doesn't answer these questions.
No, and people who are keen on the Copenhagen interpretation will they'll try to defend that. They'll try to say, that's just what physics is like. Physics is just a kind of endeavor which is dependent on measurement, and and Bohr said that physics isn't. It's not about what we can say about nature in itself. It's about. Physics is not about nature in itself. It's rather about what we can say about nature. But these have never been. I've never found these arguments particularly compelling. So.
Yeah, me neither. So, nice. And a slightly different shift to what we've been talking about. So we've been talking about quantum mechanics, the measurement problem, trying to find this solution to quantum mechanics. But one of the big open problems in physics, in fundamental physics right now, is coming up with a theory of quantum gravity, because we come up with this issue of when we try and combine quantum mechanics with general relativity and with our best understanding of gravity, we end up with problems, and no one knows how to reconcile these two theories into a different theory, or modify one into being more compatible with the other somehow. So do you have any comments on whether your new theory of quantum mechanics could give us insights or direct us towards
Right.
understanding a solution to the problem of quantum gravity.
Yeah, I suspect that it can. So, quantum gravity is not my area of expertise, so I don't want to pontificate on it too much. But something that a lot of people who work on quantum gravity say is that in order to diffuse this tension between quantum theory and general relativity, where quantum theory sort of depends on this very sort of dead and boring background space-time, whereas in general relativity, space-time is very interesting because it interacts with matter. A lot of people think that the way that we should solve that problem is by denying that space-time exists at all at the most fundamental level, by having a background independent theory where somehow space-time emerges. And within that sort of area of proposals, a lot of people like the idea that space and time should emerge from causal structure, where causal structure is this more fundamental thing. Now, the theory of causal balance is by no means enables you to describe gravity as the theory of causal balance currently works. But it is this theory in which you have, first of all, you're able to actually articulate what it means to have this fundamental causal structure, and you get events popping out of it. And so, if you are after a unified theory of quantum gravity, which also solves the measurement problem, right? If you want a theory where fundamentally all you've kind of really got is causal structure, and from that causal structure emerges these events, but also emerges the space and time in which those events live. To me, the theory of causal balance that we've currently got, it seems a very natural starting point for that endeavor. I might add one thing to that on a slightly more technical level, which is that there's this result that's often called the Hawking-Malaman theorem, which says that in the kind of most typical space-times that we use in general relativity, the phrase that's used to describe this result is often that causality determines 9/10 of the metric, which seems like a bit of an opaque phrase, but what that essentially means is the structure of space-time that people usually call the causal structure, because it sort of determines which points are allowed to influence each other. That causal structure of the space-time uniquely fixes almost all of the structure of space-time. Right, so the full structure of space-time is given by this thing called the metric, which you can understand as these 10 independent functions, functions from space-time points to numbers. And if you know the causal structure of space-time, causal structure of space-time, it's not what I would call causal structure, but if you know the causal structure of space-time, then you know 9/10 of this metric, so you know most of the structure of space-time. So that's part of the motivation for these suggestions. That causality, that space-time should emerge from causality. And that same type of structure from which space-time emerges mostly emerges via the Hawking-Malaman theorem, you find that same kind of mathematical structure when you're pinning down the causal structure in our theory. So there's really a kind of concrete starting point for where you could try to develop this kind of argument. Yeah, that's cool. Yeah, so maybe, so thinking about this theory, so you've, kind of developed this basis of the theory in your PhD, and it's kind of a research program, I guess, to continue developing it. What do you see as the most interesting or most tractable next steps, or how do you see developing the theory ongoing in the future, or what are your plans regarding what direction you'd like to take it in? Yeah, that's a good question. I think there's a few different directions that it could be taken in. one direction that I find very appealing, of course, is this kind of quantum gravity direction, see whether it actually can be used to make real meaningful progress there.
Yeah.
Another perhaps more tractable direction is I'd like to see how what we've done relates to this work that other people have done on quantum reference frames. I don't know if there's much more that I can say about that at this level, but except that the sort of idea that motivates quantum reference frames is that sort of reality can only be described from the perspective of a part of reality. There's no kind of God's eye view. And if reality is quantum, then reality can only be described from the perspective of a quantum system, which is an interesting idea. Usually, though, when people are doing quantum reference frame, it's very based on the idea of a quantum state. And I would like to see whether we can develop a more sort of causal or dynamical version of quantum reference frames. And I wonder whether if we do, that can actually help us to develop this theory of causal patterns in a meaningful way.
Right, cool. Yeah, nice. Yeah, very exciting. I look forward to finding out how these directions end up going, because they're both very cool. Nice. So I think we've covered a lot, so we can wrap up here.
Good. Okay, thank you.
So maybe we can just kind of summarize the ideas that we've talked about. So, if there was a message that you'd want to say to someone if they were just going to watch this part of this whole thing and wanted to find out what they should take away from it as one idea, then what would you want to say to summarize?
Yeah, that's a great question. I think I would say that we've struggled for a very long time to get to an adequate understanding of those phenomena that are so well predicted by standard quantum theory. And I think we'll never get to the point of having that satisfactory understanding unless we're willing to change our physical ideas in a possibly quite dramatic way. We are in a much better position to take on that challenge of transforming our concepts than we ever have been before because of some of the progress that's happened in quantum foundations over the last few decades. And I can't be sure what that conceptual transformation is going to be, but I think the main thing that I've learned from these last few years of research during my PhD has been that the arguments stack up for saying that transformation that we need to unlock a satisfactory understanding of quantum theory is to invert our traditional understanding of events and influences, to stop thinking about causation as merely a relation between events whereby one brings about another, to start thinking about causal influences as fundamental, and to start thinking of events, and ultimately all of this reality that we live in, as being something that emerges from those causal influences. That would be my message.
Yeah, very nice. So let us know in the comments if you've been convinced that reality indeed emerges from causal influences. Yeah, very cool.
Great, thank you.
So thanks Nick for joining today for this discussion. It's really cool to try and understand properly what's going on with your new theory, trying to solve these problems and the implications of these conceptual shifts and how they even relate to these really ancient philosophical ideas, but also quantum foundations progress of the last 10 years. So it's really combining some very old and very new ideas. And thanks for joining us as an audience. We will I'll put some links in the description to resources for finding out more about the ideas that we've talked about if you want to look further into it. And also feel free to let us know in the comments any questions, comments that you have. And please also join us for part 2 if you're interested in finding out the kind of mathematical description of the ideas that we've been talking about, if you have some introductory background into quantum mechanics and want to see a more precise description of the ideas there. So thanks Nick, and we will see you next time for more quantum foundations discussions. Bye.
Great.
Okay. Cool.
We might have to do another take of this. That was a really fun discussion. It's much more fun than giving a talk at a conference. Yeah, I guess I could attempt to smile. I'm way too awkward for this. You try it again. That's good. You have to send it to me so I can make it my profile picture.
Yeah. Okay. All right.